Good morning, all of you. In today's lecture, we are going to discuss various types of single electrode. So, next article is types of electrodes. We know that for the construction of an electrochemical cell, we require two single electrodes. So there are number of types of single electrodes. In case of Daniel cell, we can use the two electrodes, that is zinc in zinc sulfate, and the second single electrode is copper in copper sulfate. The left hand side electrode Zn in zinc sulfate solution. Copper can be in copper sulfate solution. So the combination of these two single electrodes, that is these two electrodes externally internally connected with each other with the help of salt bridge and externally by a metallic wire. So this is the Daniel cell. So this is the one of the electrochemical cell, and for the construction of Daniel cell, we require two single electrodes. So there are various types of electrochemical cell, chemical cell, concentration cell. So depending upon the use of an electrochemical cell, there are various types of single electrode. So first type of single electrode is the metal ion electrode. So first type, metal ion electrode. First type of single electrode is metal ion electrode. This metal ion electrode consists, the metal can be dipped into the solution containing its own ion. Metal can be dipped into the solution containing its own ion. So in Daniel cell, zinc can be dipped into the zinc sulfate solution. So this is the type of metal ion electrode. The right hand side electrode is also metal ion electrode. Why? It is because of the metal that is copper metal can be dipped into the solution containing its own ion, that is copper 2 plus. Here Zn can be dipped into the solution containing Zn 2 plus. So metal ion electrode means metal can be dipped into the solution. Which solution? Solution containing its own ion. So zinc can be dipped into the solution containing into Zn 2 plus. Copper can be dipped into the solution containing its own ion, that is copper 2 plus. So in Daniel cell, negative electrode as well as the positive electrode are of the same type, that is metal ion electrode. So all of clear to metal is in contact with solution containing its own ion. All of clear to? So there are two phases. One of the phase is solid phase, another phase is liquid phase. So this is the solid phase, is in contact with this liquid, that is zinc sulfate. But metal ion means metal is in contact with metal ion, its own ion. Zn can be dipped into the solution containing Zn 2 plus. Copper can be dipped into the solution containing copper 2 plus. So this is the type of metal ion electrode. All of clear? So example of the metal ion electrode, the first one, that is copper ion electrode. Copper ion electrode. Copper ion electrode. So we see here copper is deep into the solution containing its own ion, that is copper 2 plus. So this is the diagrammatical representation. So first of all, we are going to we can write the representation. So representation. So copper Cu is in contact with solution containing copper 2 plus. So this is the representation. All of it. So whenever we can study all the type of single electrodes, we can represent the every single electrodes. That is the representation of the electrode. We can represent according to IPC name. According to IPC, that is International Union of Applied and Chemistry. According to this, we can represent the electrode. That is, whereas the reduction reaction takes place, reduction potential is developed. So means that is we have to represent as a positive electrode. So for the representation of positive electrode, we can write first the liquid phase, then the solid phase. So this is the representation of copper ion electrode. So next we can write half cell reaction. Half cell reaction. We see here, this is the representation of positive electrode. Positive electrode means whereas reduction reaction takes place, whereas the positive potential is developed, whereas ions are get discharged. So this is the half cell reaction. Cu2 plus twice of P minus gives rise to Cu. So from this half cell reaction we can write the QA, reaction quotient. So reaction quotient, that is activity of the product divided by activity of the reactant. Activity of the product Cu, activity of the Cu2 plus. We cannot write the activity of electron. So once we know the half cell reaction, reaction quotient, then we can write EMF equation, that is Nernst EMF equation of single electrode potential. So reduction potential of copper electrode is equal to standard reduction potential of copper electrode minus 2.303 RT divided by NF log of QA, log of QA. Here activity of Cu, that is activity, as I told you in previous lecture, activity of pure metal, that is equal to 1. So 1 divided by activity of Cu2 plus. So log of 1 divided by activity of Cu2 plus. Log of here 2.303 RT divided by NF, log of QA. So what is the value of QA? 1 divided by activity of Cu2 plus. So this is the final equation. All of it. And at 25 degrees Celsius, what is the equation? At 25 degrees Celsius, this factor, that is R is equal to 8.314 joule per Kelvin, T 25 plus 273, that is equal to 298, F is equal to 96500, all of it. So this factor is equal to 0.0591. So ECU is equal to E0Cu minus 0.591, and N means number of electrons involved in it. How many number of electrons involved? 2. So that is equal to 2 log of 1 divided by activity of Cu2 plus to the base 10. So this is about the copper ion electrode, means metal ion electrode. So similarly we can write the representation of zinc ion electrode. Okay. So zinc ion electrode. Next, second type, zinc ion electrode. Zinc ion. Actually, in Daniel's cell, zinc ion electrode is negative electrode. But whenever we can study, in general, the type of metal ion electrode, the example of metal zinc. So we can represent the zinc ion electrode also as a positive electrode. So we see here we can write the representation. First, representation. That is, we can write first the liquid phase, then the solid phase. Activity of Zn2 plus. So this is the representation of zinc ion electrode. So this is the representation of positive electrode. Similar to this, so we can write means metal zinc is in contact with solution containing its own ion. So this is the metal ion electrode. Then we can write half cell reaction. Half cell reaction. Half cell reaction. So here, this is the positive electrode. So reduction reaction takes place. Zn 2 plus twice of E minus gives rise to Zn. So this is the half cell reaction. Next, EMF equation. EMF equation. So reduction potential of zinc electrode, that is equal to standard reduction potential of zinc electrode minus 2.303 RT divided by Nf log of QA, activity of the product, that is Zn, that is equal to 1 divided by activity of the reactant, that is activity of Zn2 plus to the base 10. According to this equation, log of activity of Cu, so activity of Zn is equal to 1 divided by activity of Zn2 plus. At 25 degrees Celsius, 2.303 RT divided by F, that is equal to 0.0591, and N is equal to how many electrons are involved? 2. So that is equal to 2. So final equation, Ezn is equal to E0Zn minus 0.0591 divided by 2 log of 1 divided by activity of Zn2 plus to the base 10. So this is the zinc ion electrode. Next example, silver ion electrode. Third example, silver ion electrode. This silver ion electrode consists, we can write the representation, it will consist silver, that is Ag, can be deep into the solution containing Ag plus ion, that is AgNO3 solution. So Ag plus, activity of Ag plus. Reaction, half cell reaction, Ag plus E minus divided by Ag. QA, activity of the product, that is silver, divided by activity of Ag plus. So activity of Ag, that is equal to 1. So 1 divided by activity of Ag plus. So final EMF equation, reduction potential of silver is equal to standard reduction potential of silver minus 2.303 RT divided by Nf log of QA, that is 1 divided by activity of Ag plus to the base 10. And at 25 degrees Celsius, 2.303 RT divided by F, that is equal to 0.0591. So here 0.0591 and divided by N is equal to how many electrons involved? 1. So this is the final equation. Reduction potential of silver is equal to standard reduction potential of silver minus 0.0591 divided by 1 log of 1 divided by activity of Ag plus. In general, metal ion electrode, final metal ion electrode, metal last metal ion electrode. So we see here Zn is the metal. So instead of this we can write metal, silver, copper. So in general we can write Next, is deep into the solution containing its own ion. M raised to n plus. Activity of m raised to n plus. So we see here representation of metal ion electrode. Metal, silver, is in contact with its own ion. Similarly, in general, metal, which metal? M. In general, metal is in contact with m raised to n plus. Means we are unknown about how many electrons are required for the required to discharge the ions. In Zn2 plus, in silver Ag plus. So we can write m raised to n plus. So here this is the representation of metal ion electrode. Half cell reaction. M raised to n plus Ne minus gives rise to M. Half cell reaction. EMF equation. Then we can write the QA. From the half cell reaction, we can write the QA. Reaction quotient QA. Activity of the product, that is M, divided by activity of M raised to n plus. Then EMF equation. Reduction potential of metal ion electrode is equal to standard reduction potential of metal ion electrode minus 2.303 RT divided by NF log of, here activity of pure metal M is equal to 1. So 1 divided by activity of M raised to n plus. So QA is equal to 1 divided. So log of QA. So 1 divided by activity of m raised to n plus to the base 10 at 25 degrees Celsius. 2.303 RT divided by F is equal to 0.0591. So final equation, reduction potential of metal ion electrode is equal to standard reduction of metal ion electrode minus 0.0591 divided by n. So we are unknown about how many electrons are required. So we can write n as it is. Log 1 divided by activity of m raised to n plus. So this is the final equation. All of clear? So reduction potential of metal ion electrode, this value is constant. All the values are constant. If you keep the temperature constant, this value is constant. N number of electrons will be constant. So reduction potential depends upon the concentration of the ion. Or in other words, we can say that this metal ion electrode is reversible with ion present into the solution. All of clear? And this metal ion electrode is reversible with positive ion. All of clear? So we can write the representation. Then we can write half cell reaction. From this half cell reaction, we can write the reaction quotient. Reaction activity of the product divided by activity of the reactant. Activity of the pure metal is equal to 1. So 1 divided by activity. From this QA, we can write the EMF equation. So if you want to write the EMF equation, we have to know the half cell reaction. We have to remember that. Half cell reaction. Then we can write EMF equation. 2.303 RTF at 25. This value is equal to this. This is the standard potential of the metal ion electrode. Means reduction potential of the metal ion electrode depends upon activity of the metal ion present into the solution. Okay? I will continue in next lecture.